All right. This example here, this warm-up, is really example 7 from your notes from 2.5. Example 7 from your 2.5 notes. I just kind of modified it because we're not going to get into the composition. Example 7, section 2.5. Okay, so Mr. Johnson taught y'all about inverses. And do y'all remember, did he say what an inverse is or what the purpose of an inverse is or what it does? It could be the opposite. It could be the opposite. Like if you were adding 5 and you wanted to undo that, you could do the opposite of adding 5, which is subtracting 5, right? But it's not always the opposite. We call those operations inverse operations, okay? So someone said, what, graph? What do y'all say? Good. If you have an inverse and you want to see what the graph of the original function was or vice versa, all you have to do is reflect the graph across the line y equals x. And when you do that, all of the x information and y information exchange. So the x-axis becomes the y-axis becomes the x-axis. The y-intercept becomes an x-intercept. The domain of one becomes the range of the other, and vice versa. Okay? And in order for that graph that's reflected across the line y equals x to pass the vertical line test, after you reflect it, it would be the same as if that graph passed the horizontal line test before you reflect it. Because vertical lines and horizontal lines trade places across the line y equals x. And so that's why he said, if you want a function to have an inverse that is also a function, the original function must not only pass the vertical line test, but also the horizontal line test. And those types of functions, he said, were what? What? Ladder? No, he said they were one-to-one. They're one-to-one functions, okay? So to be a function, it means that every x can only have at most one output. But to be one-to-one, every y value can come from at most one x value. That means it has to pass the horizontal line test. And because that horizontal line, when you reflect it across line y equals x, becomes a vertical line test, it's kind of like testing for a function before you reflect it. All right, so if all the x and y information interchange, that's how we're going to actually algebraically find the inverse. But you already have a very intuitive idea of what an inverse is. For example, if I'm thinking of a number and I don't tell you what it is, but I tell you that I'm going to take my number and I'm going to multiply it by 5, and then I'm going to subtract 5 from it, and then I'm going to divide it by 3. If I tell you that that number is 15, could you tell me what my original number was? You could. What would my original number be? If I took a number, I multiplied by 5, subtracted 5, and divided by 3 in that order to get 15, yeah, it's 10. How did you do it? What did you do? Intuitively, you multiplied by 3 and then added 5 and then divided by 5, right? So what you did is you did what we call the inverse operations. An inverse operation essentially undoes the other one in the reverse order. In the reverse order. So if I'm going to write my function, let's call my function f of x. I'm going to take my input x, I'm going to multiply it by 5. That's 5x. Then I'm going to subtract 5 from it. And then I'm going to divide the whole thing by 3. And that's how I generated my 15. You intuitively found my number. We call that f inverse. Okay, that little -1 between the f and the of x, we read it as f inverse, not the reciprocal. And you took my output and you multiplied it by 3 first. You added 5 to it, and then you divided it by 5. Those two functions are inverses of each other. They undo each other's work. Okay? Plug one into f, you get an output. Plug that output into f inverse, you get back your original input. So why is this important in today's day and age that we have inverse functions? Well, imagine that you coded a message, but there was more than one way to decode it, right? Like if you code a message with x squared, and I tell you I square a number and I get 25, could you tell me what my original number was? What number did I square to get 25? No, it wasn't 5. It was -5, right? So the graph of x squared does not pass the horizontal line test, so it's not one-to-one. Now, he did talk about restricting domains, and you can make it one-to-one, but in general, x squared is not one-to-one. So that would not make a good coding, decoding system, right? But one-to-one functions do. There's only one way to code the message, and there's only one way to decode it. And so everything that gets sent over the internet is encrypted, right? And imagine if there was more than one way to decrypt something after it's been encrypted. All right, so that's what we're going to do. He told you algebraically, so that you don't have to rely on your intuition here, he told you algebraically how to find an inverse, and it was a review, because I think you had it in Algebra 2. The first step for me is calling f of x y, because remember, f of x is just a fancy way to say y. The next step is the money step. When we reflect the graph across the line y equals x, all of the x and y information interchange, okay? Which is why y equals x is the mirror for the reflection, because it is its own inverse, and it keeps the sign. So the money step is to interchange x and y, or switch x and y. Now, all you have to do is solve for y. Now, the reason this works is because in solving for y now, you're peeling back the layers by doing what? The inverse operations in the reverse order. When you algebraically learned to solve equations like this, you were solving them, peeling back the layers by doing the inverse operations in the reverse order. So that's why algebraically it works. You don't have to rely on your intuition. So the last thing I did when I plugged it into my original function was subtracted 5. That was the last thing I did. What would be the first thing you would do if you were solving for y? You would add 5, okay? So I'll go ahead and do it this way. We get x plus 5 equals negative 2 cube root of y minus 1. All right. The second to last thing that I did when I was plugging it into my original function was multiply by negative 2. What's the second thing you're going to do? Divide by negative 2. We're doing the inverse operations in the reverse order. So that gives us x plus 5 over negative 2, and then those divide out, and we're left with the cube root of y minus 1. The third thing I did was take the cube root of something, which means now the third thing you're going to do is, in the reverse order, is what? Cube it, right? Again, you're doing the inverse operation essentially in the reverse order.
Teachers, please pardon this interruption. Just quickly, would you please release the varsity tennis players at this time? Thank you.
Oh yeah, where y'all going? Y'all's tournament is back on. Okay, I'm recording it right now, so you want to check out the rest of the recording because we do have a test tomorrow. Okay, and good luck. All right, soggy tennis balls are not really fun to hit. Okay, the very first thing I did when I plugged in was subtract 1, right? So what is the very last thing that you're going to do? Add 1. Again, we're doing the inverse operations in the reverse order. So we're left with x plus 5 over negative 2 cubed plus 1. Now, instead of calling that y, we're going to call it what? Good morning. Yeah, let's rename it. What did you call it, though? F of negative x? We don't call it that. What do we call it? F inverse of x. F inverse of x. So we reuse the name f to show that it is related to f, but we have to call it something else, right? That shows the relation of how it's related, and it's the inverse function. Now, one thing Mr. Johnson did not have y'all do the other day, which I wish he would have, was to verify. Okay? You could verify that it undoes the work. So let's go ahead and do that. Let's plug in a number into our original function here and see what we get out. We got to choose something nice, like f of 9. Go ahead and plug in a 9 for x. Thank y'all, girls. Good luck. You're practicing with the water there. Yep. What do you get when you plug in a 9? You got what? Ethan, what'd you get when you plugged in a 9 up there? Okay, you haven't finished. Good. You don't have to show all your steps. We can do this one together, right? 9 minus 1, 8. cube root of 8. 2 times negative 2. Negative 4. Negative 4 minus 5. Negative 9. Okay? So on the graph of f, there's an ordered pair called 9, negative 9. What would the corresponding point be on the graph of, I won't call it G yet, on its inverse? What do you think? Yeah, negative 9, 9, right? All the x and y information switches. Let's verify it. We have our function down here, f inverse of x. Let's plug in a negative 9. If it works, we should get a what out? A 9. Fingers crossed. Let's do it together. You don't have to write down all the steps. Right? Negative 9 plus 5. Negative 4 divided by negative 2. 2 cubed. My fingers are crossed here. See? 2 cubed. 8. 8 plus 1. 9. Yeah. I just had my fingers crossed for effect. We knew it was going to work, right? Yeah. So we got back our 9. So we could do that all day long. We verified it. These are, in fact, inverses of each other. Okay. So he didn't do that the other day, but now you all know it. Now here's the property. I think he did show this to you. Two functions, we call them f and g, are inverses if and only if this is true, right? So he mentioned this to you, and he told you that the little open circle, of course, is what? It means right. And we've had this before as well. This was the condensed version. So if you write it in the expanded version, it would be this. Okay, and so now you can clearly see which function is inside of each other. So this is composition of functions, and is composition of functions in general commutative? Does the order matter in general? What was Mr. Johnson's first example to y'all about the season pass to Schlitterbahn? Remember that from last Thursday? You got a 10% discount versus a $10 off. Did it matter the order? It did, right? So that's composition of functions. You got a different result. It was better if you wanted to save money to do what first? The percentage discount, right? Or the $10 off. No, it would be the percent, right? Because you're taking the percentage off of a larger number. But the point is that it matters, right? You didn't get the same answer. So composition in general is not commutative, but it is commutative only when G and F are what? What does this theorem say? Only when they're inverses is it commutative, which means you can actually do either one first. And I'll prove it to you right here. He didn't do this, but I'll do it. Let's say I'm standing here and I have a simple function that sings the lone sick blues. Yeah, very good. I'm going to take one step to y'all's right. And what's the inverse of one step to the right? One step to the left. Where am I standing? Right back where I started, at X marks the spot. Now, does it matter the order? What if I took one step to y'all's left first, and then one step to the right? Doesn't matter. I'm right back where I started. Now, Mason Ramsey could add that to his act, couldn't he? That dancing, right? But he didn't do that in the Walmart. He just stood still like this and kind of went up and down, right? Yeah. Okay. So composition is commutative. When the two functions are what? Inverses. All right. So that's reviewing Mr. Johnson's lesson. Here's example 8. Your test is tomorrow. You're going to have one multiple choice question like example 8. This is the only thing from 2.5 that's going to be on y'all's test tomorrow from Mr. Johnson's lesson. And I think he worked one like this, but I want to emphasize something. Let H be the inverse of G. Okay, so G and H are inverses. It says to find H. All right, so algebraically, how are we going to do that? What's our first step? Switch X and Y, but I don't have a Y. So my first step, which kind of just primes the pump, is just to call G of X or F of X or whatever it is, Y. So now you're staring at a Y. Now that step is optional. I know y'all could do it without that. But here's the money step, right? Cha-ching. Interchange X and Y. And so now in solving for Y, remember, we are doing the inverse operations in the reverse order, just like you learned in Algebra 1. He went through the algebra with you. I got to get these Y's by themselves. How did we do that? They don't just divide out, right? See, that's funny now, right? At the beginning of the year, some of you are like, why is that funny? But now we know it's funny. That's also funny. All right, what do we do here to solve for y? I got to get a single representative of y. Divide by 2? No, you can put this over 1. What did y'all do in class today on Thursday? Do you have y'all's notes from him? No, there's no complex fraction here. If you put x over 1, you're staring at a what? Proportion. And how do we solve proportions? Cross multiply. Right, so let's do that. So you're going to get x times the quantity 4y plus 3 equals 1 times the quantity 2y minus 1. Okay, so I put parentheses there, right? They're your best friends. And now we distribute the x, and we get 4xy plus 3x. And then distributing the 1, of course, is just that. So now we have everything on the ground floor. Our goal is to solve for y. We have 2 y terms, don't we? Got to get them together. So let's get them over here on the left. Bring the 2y across, and we'll bring the 3x across, since he doesn't have a y. So we've done this before this year. What's our next step? How do we get a single representative of y? What's that? Well, the greatest common factor would be 2y, so I could factor out a 2y, but my objective here is just to solve for y, so let's leave the 2 in there. Let's just factor out the y. Normally we would factor out the 2y. So here we're left with 4x minus 2 equals negative 3x minus 1. And now we're rounding third, heading home. The Astros are going to win. They're going to win. And we end up with that. So now we solve for y as a function of x. So what was the last thing we did? We want to give it its new name. It is the inverse of g, so you could call it g inverse. But that notation is sometimes cumbersome, so we renamed it, right? If your parents named you g inverse, you might want to be renamed h, right? It's marginally better, right, Ewan? So let's call this one h. So tomorrow on the test, I may either have you find the inverse, or I may ask you the following question. What did we say happened to the domain and range of inverse functions? They flip, right? They interchange. So let's come up here. Let's find the domain of g for the original function. And you can either do it in your head, or you can set it off to the side equal to 0, whatever you want to do. What's the only value that's not in the domain? Louder? Not 3 over 4. Negative 3 over 4. Right. If you need to still go off to the side and set it equal to 0 and do your algebra, that's fine. But x can't equal negative 3/4. Now, normally we get the range from the graph, but we can get the range from here because we know what's happening. What would the limit as x goes to infinity be here? Because remember, that's the existence of a horizontal asymptote. 2 over 4, which is a half. So it's okay for a graph in general to cross its horizontal asymptote, but these types, from our experience, do not. So what's the only y that's not in the domain, or the range, sorry? 1/2. Okay, so if what I said was true, that domain and ranges switch, then the domain of g should end up being the what of h? The range, right? And the range of g should end up being the domain of f. Let's verify that, because we have h right here. Let's do it down here where we can see it, and then we'll bring it up to the top. What's the domain of h now? Set of all x such that x ain't what? Not negative 2/4. Be careful. Again, like I said, if you need to, go off to the side, do your bench work. Say that the denominator can't be 0. At this level, you should be able to do that in your head. Okay? This is pre-AP. Bring the 2 across. It becomes positive. Divide by the 4, you get what? 1/2. So that's the only value that's not in the domain. Now for the range, we'll do it the same way. Where's the horizontal asymptote for h? Remember, the limit as x goes to infinity, all we're looking at is the leading terms. Good. They're both to the first, so it's leading coefficient over leading coefficient. X can't be negative 3/4. We get that from the actual equation. Now, since we have tunnel vision, let's copy those and bring those up here and set them side by side. The domain of G, did it end up being the range of H? Everything but negative 3, 4? It did. And the range of G, did it end up being the domain of H? It did. So, on the test, if I give you G of X and I ask you for the domain of its inverse, do you have to actually find the inverse and then find the domain? Or is there another way to do it? There's another way to do it. If I ask you for the domain of the inverse, it should be the what of this? The range. And you could see, oh, the range is everything but 2/4. Okay? Similarly, if I ask you for the range of the inverse, you don't have to find the inverse and then look for its horizontal asymptote. The range of the inverse should be the what of this? The domain. Okay? Keep that in mind. That's the type of question you're going to have on your test tomorrow. Let's practice. For your test, then, if you go to the old test page, and I told you on Friday after we graded the group quizzes that you can look at 2.1 to 2.3. For the most part, those questions are going to come from there. Your free response is going to be almost identical to your group quiz. But there is one question from 2.5. So if you want to practice that, go to the 2125 2017 test. Okay, 2.1 to 2.5. There's only one question that's outside of 2.3. And if you look at number 4, look at question number 4. It says, if f of g of x equals g of f of x, what does that mean? That they're inverses of each other, right? That's what that means. And if g of x is equal to that, what's the range of f? It's inverse. We do not have to find the actual equation of f. So begin with the end in mind. If we're looking for the range of f, it should be the what of g? The domain. And what's the only value that gives you division by 0? Negative 5/7, right? Negative 5/7. Is that an answer choice? Everything but negative 5/7? Yeah, it's answer choice B. Okay? So that's the type of question. For what it's worth, I asked you for the range of f. What would the domain of f be? The domain of f would be the range of g, which is everything except what y value? Negative 3/7. Good. The value of the horizontal asymptote. You get it? Now notice that's another answer choice. So you got to make sure what I'm asking. But it's easy to remember because they're switching, right? So that's all that you're going to need from this test here. That's all you're going to need. If you want to go back, there's like 3 more tests. Let's do the 2015 test. And this is the last one I'll do. And then you can practice with the other 2. Look at question number 5. Go ahead and do question number 5. You'll have one like that. What'd y'all get? It's also B, right. The range of G inverse. Now on this one, I just flat out told you G inverse. I didn't give you the composition. So the range of G inverse is the domain of G. The domain of G is everything except the value of x that makes the denominator 0. So it's everything but 7/3. What would the domain of G inverse be? Good. Everything except what? Negative 5/3. So notice they're not written in the right order. The leading term in the top is the second one. So there's a horizontal asymptote at negative 5/3. So that's the range of G, so that would be the domain of G inverse. All right. Everyone good on that? All right. Well, that's it then. The rest of the questions you can kind of practice if you want from 2.1 to 2.3. There's the 2017 test. You'll have a graph. I'll ask you for some more limits. Be careful when it talks about of and at. When I talk about local max and local mins, like on question number 4, I wrote it, bless you, I wrote it back here on the board. It is in your notes. But when we talk about local or absolute max or mins, when we say at, we mean the x value. At x equals. If we say of, it means the y value. So if you notice on part B, it just says local max of 4. I didn't put y equals 4. I don't have to put y equals 4. Okay? The of is talking about the y value. The at is talking about the x value. So you have to be reading very, very carefully because there's one that says at and there's one that says of. So that one little word can mess you up tomorrow, but hopefully not. All right.